Hey everyone, how's it going?
Hello.
So we'll get started in a moment, but while you're all getting situated, if it's not too invasive, I would really appreciate it if you can put your cameras on. I can actually see you all on my monitor. That would be awesome. If it's not convenient, it's okay, but it's definitely great to see you all. Yeah, I can see that you're mostly on mute, so just be aware that when you come into the room, by default, you're going to be on mute just so that we don't have everybody talking over each other. So just keep that in mind. I'm sure it'll happen a lot this semester to me, that unmute yourself before you start talking. Okay, well, awesome. Well, welcome everybody to Math 3200, Ordinary Differential Equations. It's great to see you all out there, wherever you might be. I just want to take some quick attendance just to make sure I have everybody's name pronounced correctly. And also, just so you know, I'm recording this. I'm going to record every class, and you might just want to smile because I'll probably use some of these screenshots just to make a little diagram of your faces next to your names. That's how I'll learn them, since I won't be necessarily seeing you all class long. So please, if you go by a nickname, correct it. You're welcome to change your name in the participants box. So if you click on participant and you hover over your name, there's an option for more, and you can rename yourself to whatever. And so if you want to just put your nickname in, add some pronouns, whatever you want to do, you're welcome to do that. So please just let me know if I mispronounce your name. When I do call your name, please just unmute yourself and say hi so I get you on camera. That would be great. So let's see. Zhao Yuan, last name is Bao.
Yeah, here. Hi.
Hello, nice to see you. Vinay.
That's my middle name. First name is Shamik.
Shamik, sorry, I skipped that part.
Yeah, you're good. Nice to meet you.
You prefer your first name over the middle name, yes?
Yeah.
Okay, Shamik.
Nice to meet you. Yeah.
Got it, nice to meet you. Marissa?
Hi.
Hey, Marissa.
Hi.
Welcome.
Thanks.
Yep. Xiaohan Chen is the last name.
Hi.
Hello. Did I pronounce that correctly? Xiaohan?
Yeah.
Okay, awesome.
Xiaohan.
Great, nice to see you. Yu Cheng. Okay, Yu, last chance. And then there's Yuaban Cheng.
Hi, I'm here.
Hi, Yuaban, nice to see you, sort of. I know that some students are actually in China, for those of you, and it's quite late over there. So I understand you might be in your pajamas or something like this. Okay, Brian Heckman.
Here.
You mind just saying hi again, Brian?
Hello.
Hey, Brian, nice to see you. Kenneth.
Hello, sorry about that.
That's okay. Say hi again, Kenneth. Sorry.
Oh, hey, do you want me to?
Yep, got you. Hey, Kenneth, nice to see you. Christina, Jessen.
Hello, right here.
Hey, Christina. You
Hello.
look like you're someplace up in the mountains. Is that an actual?
It's a virtual
I
background.
was gonna say, it looks like a really dangerous place to be learning math. That's good, okay. Nice to see you. Molly Kettner.
Hello.
Hey, Molly. Yua Lee.
Hi.
Mind just saying hello again, Yua?
Yeah, here.
Oh, hi, Lee. Yeah, and so, yes, if you just want to raise your hand when I call your name, that's fine. But again, if you've got your camera on, it's great just to catch a little screenshot of you. Eric Lormore. Mind just saying hi again, Eric? Okay, no problem. I see you, gotcha. Yukiyu Ma is the last name. Okay. Shihen, I think. Last name is Mao.
Yeah. Hi.
You mind just saying your name? I want to make sure I have it correctly.
Yeah, Shicheng Mao is right.
Say that again, sorry.
Shicheng Mao.
Gotcha.
That's correct.
Okay,
Thank you.
great. Thank you. Reem?
Hi.
Hi, Reem. There you are. Hi. Rachel Parsons.
Hi.
Hey, Rachel. Max Richmond. I don't know if you've got a hand up. Okay, Max, last shot. And Cortez, I think I saw you around
Here.
Hey, Cortez.
How's it going?
Good. How are you?
Fine and dandy.
Good. Kyle Redmond.
Good morning, Dr. Ziegler. How are you?
I'm good. I think
Spiegler.
yes. Hey, nice to see you, Kyle. Kirsten, excuse me. Kirsten. Last name is Soles, I think. Kirsten. Hey, nice to see you. Abraham Stokes.
Here.
Hey, Abraham.
Present.
Jet Vu.
Hey.
Hey, Jet. Z-Way. I think I see you here someplace. Gotcha. Thank you. I see your hand. Izzy Williamson. Izzy.
Sorry, that's me.
Hey, Izzy. Nice to see you. Austin. Austin Urosh. Okay. Yunchi.
Hi.
Gotcha, Austin. Thank you. Yunchi, sorry. Where I think, hey, hello. And Linren.
Yeah, hi. I'm here.
Okay, great. All right. Is there anybody else? I think we've got everybody. I checked just before class started, but if anybody else is here, you're welcome to chat. I will just say, yeah, so welcome everybody. I guess I should say that. So my name's Adam Spiegler. I'm your professor for the semester. I would prefer it if you all just call me Adam, honestly. That's what I am used to. If you want to call me something other than that, please make it nice, especially if it's to my face. Professor Spiegler is fine, but again, I prefer Adam among all of those. And so I made a little video if you didn't get a chance to see, in case you're curious about me. I've been here 3 years. This is my 3rd year here. And so I also direct all of our undergraduate programs in the math department and do all the advising. So some of you I've had in classes before. It's great to see you again. Even more of you I've probably interacted with as an advisor. So great to have you in class. So if you do have any questions about our degrees or any advising questions, I would be the contact for that as well. I want to just kind of first go through how the class is going to be structured, since I know that this might be done differently by different professors, and give you a chance to ask any questions about how the class is going, and then we'll get started with the material. And so there's a lot of ways that we can interact on Zoom, and so I definitely want to take advantage of that. We'll definitely be doing some work in breakout rooms, so you'll get a chance to talk with some of your some of your classmates in addition to me. So if you do have any questions, honestly, the best way that I'm going to see it or hear it is if you just unmute yourself and talk. And I know that it's hard when we want to avoid talking over each other, but it's going to happen, so that's fine. You can raise your hand. I'm less likely to see that, though that's pretty easy to catch as well. You can also send things into the chat. I'll just say when I have a PowerPoint up and I'm talking and I'm annotating that, it's hard for me to read the chat at the same time. So please just talk is the best way. And I don't care if you talk over me. That's totally fine. But you're welcome to use the chat and the hand raise. If I don't see them, I'm not ignoring you. I just haven't had a chance to look at them yet. So keep that in mind. And there is a little hand wave that you all can do So that's also something good to make sure that you're familiar with. Okay, so are there any questions so far before we get going? Okay, so let me get back into my slides. Okay, so one thing that I just want to point out is all of the slides that we're going to work through, mostly we're going to be doing worksheets together here, are posted in Canvas in the module. So I will take us over to Canvas in a second to show you how things are organized, just so that's clear. But I think it would be a good habit to get the slides open on your computer or print it out if you have access to a printer, get the worksheets downloaded ahead of time, because when I put you into breakout rooms, you'll lose the screen share. So if you're looking at a slide when we're all together and I put you in a breakout room to talk about a problem, hopefully you have someone in your group has the problem. So it will be useful for you to have the materials while, oh, these are the wrong notes, wrong class, sorry. These are the ones that we want. Okay, so let me get back to here. Okay. So yes, this is the class. Sorry if you thought you were in the wrong class. This is Math 3200. I am also teaching Math 3000, so I may see some of you later. But most importantly, the best way to get in touch with me is by using my email over here. My office hours, just so you are aware, it's a different link than where we're meeting for class. So office hours link is over here. Our class is going to meet in this same link every single time. So that won't change. I've got office hours Tuesday, midday, Thursday in the morning. I'm happy to meet with you at just about any other time. Yeah, Cortez, question?
And you said this is all downloaded on Canvas?
Yes.
For us to view? Okay.
Yes. Yeah.
Thank you.
Yep. So everything that we go through in class is posted ahead of time, and whatever I mark up, I can upload afterwards. So you have the annotated version as well. Yeah. Okay. So yeah, and so I would say it would be great. I would love a chance to get to know all of you this semester, and when we're all here together, 30 of us, it's a little bit more challenging. So I'm happy to talk with you about anything. So this is not just for students that are struggling. This is for anybody, whether it's you've got an A- and you want to get an A, or whatever the case might be. So you're welcome to come by, set up an appointment. Happy for that. So for the grading scale for the semester, we have 2 exams during the semester. Those dates are posted on the syllabus as well as in Canvas. So if for some reason that has to change, I will let you know, like not the day before, but like a week before at least. I'm not planning to shift those. I will say, and there's a 3rd exam during finals week. That schedule has not come out officially yet. I'll just say that it's likely that our exam, since our class meets on a Monday, Friday, it's either going to be probably on the Monday or the Friday of Monday or the Wednesday of finals week. That 3rd exam is not a final exam in the sense that it's not going to be comprehensive. It's just going to cover the material that we've done after the 2nd exam. So that's why it's worth a little bit less, because it won't be as much material on that last exam. Otherwise, we've got homeworks that are going to be due basically once a week. The first homework assignment is up, and it's due a week from today. So homeworks are going to generally be due Monday at midnight. So it's not due before class, it's due afterwards. So the idea is whatever stuff we cover this week, you're going to have a homework assignment on that's due on Monday. So just be aware that some of the stuff on the homework assignment might not make sense until we discuss it on Wednesday. So if some of the problems look different, it might not be that you missed something, it's just we haven't gotten to that just yet. And lastly, in addition to the homework, there's going to be a brief reading quiz before each class. So by brief, I mean 3 or 4 questions, multiple choice, fill in the blank, where you've got multiple attempts to get the quiz questions right. So the idea of the quiz here maybe isn't the right word. It's more practice. So I'm not, if you get it wrong, you'll get some feedback and then you get a chance to correct it. And you don't get penalized whether you get them on the first shot or the second shot. You have 3 attempts to get them right. So I'll just keep that in mind. So I'll take you over to the Canvas page in a minute just to show you where to get those. So these are going to be due before class, most classes. So you should expect every Monday and Wednesday to have one of these done by 10:45, since we meet at 11.
Can I ask you something about that, Adam?
Yeah, of course.
So for the homework and the quizzes, are you okay with taking it with a classmate, collaboration, or just on the homework? What does that look like?
Yeah, so you're allowed to collaborate on everything except for the exams. So you're welcome to work on homework problems. You're welcome to do the quizzes together. I'll just say the quizzes might be slightly randomized so that some of the numbers are slightly different on different versions, but the problem itself would be essentially the same and the solution method would essentially be the same. So yeah, you're definitely welcome to work with each other on homeworks and quizzes, but everybody's going to have to hand in their own individual work. So even if you're working with somebody, you each need to write up your own solutions. And I can tell you, show you how I'm hoping you guys submit your assignments electronically in Canvas. Okay, any questions? Okay, so the kind of last note, and then I'll take us into Canvas, is there's a textbook for the class. It's called Notes on Differential Diffie-Qs, and it's open source and free. So I sent you all a PDF by email, but the PDF is also in Canvas. So you don't have to buy anything. They do make a paper copy. Here it is. It's actually pretty nice. It's a paperback copy that I think I paid 18 bucks from Amazon for. So if you do want a paper copy, they are available. And maybe that's nice if you want to like mark it up while we're talking on Zoom. That's a possibility. So it's not that expensive, but you definitely don't need it. So you don't need to buy anything else for the course. Okay, questions? Okay, so let me go into our website just to show you how I think about what kind of I envisioned when I created the Canvas page, and how I might suspect you can kind of navigate the page. So here you guys can see Canvas, right? Want to make sure you're looking at the right screen. Okay, so most of the stuff is going to be found in the modules. So after this week, I'm going to change the course homepage to the modules because that's where you can find most of the material. So here are the materials for week 1, and the subsequent weeks are going to be organized the same way. So for each week, you should have most of the content uploaded at least by Sunday before the week starts. And I just tried to break things up into, here's the readings from the textbook that you might want to look at. Here's what we're doing on Monday. Here's what we're doing on Wednesday. Here's what we're using in Zoom. Oh, I'm sorry. I guess I didn't put these notes up on Zoom yet. I can add them up, sorry. But we'll be working with this worksheet, what is a differential equation, shortly. And then for Wednesday, here are a couple of videos that you might want to watch, or you can read the book in order to do the quizzes. So these videos for this week are Khan Academy videos. They did a very good job of being straightforward. I think after a week, I'm going to be creating my own video. So I have a bunch from when I taught this in the past, and I'll probably be creating some new ones as well. But for this week, it's just a couple of Khan Academy videos. And then there's a quiz, a pre-class quiz over here. So here you can see this is due Wednesday, 10:45. So any questions as far as organization? Yeah, and so homeworks and quizzes are down here. So for the homework assignment, homework 1 is up. The instructions, yes, there was a hand. Cortez, yes.
So the way this is going to be structured, then it's going to be we're going to watch like the Khan Academy videos you said, and then do the homework, or
so most of the time the videos are going to be me. Unfortunately, you're stuck listening to me. This week's they happen to be Khan Academy, just because I think the material at the start is a little more straightforward, and there's already very good videos on them. Once we move past a week or two, we're going to be beyond content that I can easily that I would want to use from somebody else. So I'll be creating my own stuff. But the idea is you don't have to watch them. You can read the book instead if you prefer to read, and then answer the quiz, or you can watch the videos and answer the quiz. I would suggest trying to do both. Try and read and watch the video, and then give the quiz a shot. So the quiz is not going to be the trickiest stuff, right? So I think sometimes in classes, the problem is you go through some of the more basic stuff together in class, and then you work on homework problems that might be the more challenging stuff that you didn't get time to do in class. So I want to do, if you've heard of this flipped classroom, that's kind of the idea here, where I want everybody to come with some background in the stuff that we're going to be talking about. So kind of get the basics down that I think are that are more easily delivered in a video that you can watch asynchronously at home. And then we'll work on some more difficult problems together in class where it's good to get that in-time feedback. So that's how I kind of envision that.
All right, thank you.
Yep. Were there any other questions? Yeah, so there was a question about, so are we not required to take the Zoom meeting? So yeah, so the idea with that is we're not going to be doing the same thing in Zoom that's being done in those pre-videos. So if you're only watching those videos and not coming to class, or at least watching the Zoom recordings of class, you're going to be missing a lot. Yes, so we're going to be working on some of the more difficult concepts in Zoom. So they will be different ideas. Okay. Any other questions? Okay, so if you're kind of looking at the instructions here, this is going to pretty much be the same on all of the assignments. But what I would prefer you all to do is upload your work into a single PDF file. So you don't need to type it up. You can write it by hand. You can take pictures of your work. And I put some links here to some free apps that will kind of take all of your photos if you take them on a phone and scan them and create like a scanned PDF document. So for me, that's the easiest stuff to look at in Canvas when I'm trying to grade. So that's what I'm asking you to do. And down here, there are instructions like, yeah, you're definitely allowed to work with other people, but just make sure that the work is your own, that you submit. And in order to submit your work, you would just click this submit assignment button, and then it's going to ask you to upload a file. So you would upload your PDF file, click submit, and that's it. Any questions about that? Okay, and then as far as the quiz goes, we can click on this. Here are some instructions. Here is the reading material that the quiz is going to be on. Here are a couple videos that you can watch to help as well. But when you're ready to take the quiz, this is what it looks like. So this won't make sense now, but hopefully after watching the videos, it will. So this one has 4 questions. 2 of them are multiple choice. 3 of them are no, yeah, 2 of them are numerical answers. And again, you have multiple attempts to do this. Okay, any questions?
Yes. When will the pre-class quizzes open?
Yeah, so my goal is that they're open. So like we've got class now, and when class wraps up, it should be open for you to do, if not already, within an hour after this class is done. So yes, I realize people have got busy schedules. So I don't want to open them like 20 minutes before class starts. That's kind of rude. So I will try and have them ideally done so that when class is over, you'll see it open already. That's my goal, at least.
Okay, thank you.
Yep. Okay, any others before I go back into my slides? Okay. Okay, so yeah, so just some kind of guidelines. We've talked about some of this, but I would prefer if you can, excuse me, have your cameras on and keep your mics on mute when you're not talking. And I'll just say, for the cameras being on, I don't know, I took some notes on a napkin as to why I like that. And it's just that, it's really helpful for me to see your reactions. So, that visual feedback is really useful for me. When I'm in a class, I can smell the fear and I can smell the confusion. I can't do that over online, but I still can see your faces. So it's a bit lonely being here alone all day. So it's nice to see other people. And it also helps me from a teaching point of view when I can get that interaction. So, you wouldn't like it if a professor necessarily had their back turned to you the entire class. So it kind of feels almost the same way over here. So I don't want to make anybody uncomfortable if you don't like to do that, but if you can, that's great. Yeah. So in addition, there may be times where I'm going to be cold calling on people. And again, this is not to put anybody off or put anybody in an uncomfortable position. It's just that when I ask a question, I don't want people coming in and kind of talking over each other. So I want to make sure that people are following along. That's why I ask questions. It's not to check your knowledge. It's just to see whether or not we need to spend some more time on something. So sometimes we'll have polling questions to do that. Sometimes I might just call on some of you. And then one last thing I think I want to talk about as far as the logistics. Zoom is actually really good. I was expecting bad things in the spring with like the whole world going on to virtual learning. But I promise you it will crash at some point for me this semester in the middle of one of our classes, unfortunately. And it's likely to do it for you as well at some point. So if it happens to you, I guess it's not as bad. It will disrupt you. If it happens to me, it's bad because it disrupts everybody. And so I suspect that if I get kicked off of Zoom, I think you all will the room will still be open. So please don't go anywhere. Just hang out, chit chat with each other. The room will still be recorded. So just be aware of that if you're talking with each other. And I will do my best to come back in as soon as possible. Usually it's just close Zoom, reopen Zoom, and I'm back in a minute or two. If I'm having a more severe problem, then I'll post an announcement in Canvas if I can. Like if my internet is down, I can use my phone and post something on Canvas. So that's how I'll let you know if it's like, I'm totally down, I'm not gonna be back for a half hour, class dismissed kind of thing, but hopefully it doesn't come to that. Usually these are really short issues. If it happens to you and you're worried about what to do, usually again, it is just log off of Zoom and log back in, and that works. If it doesn't, try restarting your computer. If you have an internet signal, the problem very well could be you don't have an internet signal, in which case there is an app, Zoom app, that you can use on a phone, which at least you can then get in on your phone using a data plan, which might not be ideal, but at least you could follow along with class. Classes will be recorded as well, and I'll post those recordings online. Okay, so I just saw the next slide is math. So before we head in that direction, any other questions about logistics of the class? Okay, so let's kind of start with, so actually this material over here is in the introduction of the differential equation reading materials. So the introduction, kind of the first section, is really for an instructor that's trying to tell, here's how you should use the book. And then the next section is what is a differential equation and some terminology. So let's just kind of think about a problem that you may have seen in previous math classes. So we've got a rectangular pool. One side's going to be, in this case, 4 feet longer than the other. Write an equation for the area as a function of x. Okay, so for this, right, we would say area 96 feet squared equals the product of the dimensions of the pool. So this is not a differential equation. Okay, let's start by saying what a differential equation is not. So this would be an example of what we would call an algebraic equation. So I just want to kind of say that with algebraic equations, there are certain tools that we're already comfortable using to study those relations, and these same tools we're going to use in differential equations, just the equations are going to be different. So for example, we can draw a picture to help us set up the equation. That's going to be useful when we're modeling differential equations. So I could have drawn this pool if I wanted to, and said, okay, here's x, and here's x plus 4, and therefore the area, if it's 96, is going to be x times x plus 4. So drawing a picture might be that. Drawing a picture might be sketching a graph of the function with some quadratic thing. So we can use pictures to set up the model, and then we can use graphs to try and understand the behavior of the model. And so, right, so even if we couldn't solve this equation, it's real easy to verify whether something is a solution to it or not. We just plug it in and check. So we're going to work on similar things with differential equations today. And so sometimes, even if we can't solve things, we still can say something about the solutions, like x is between here and here, or these sorts of things. So there will be plenty of times where we have a differential equation and we don't have the tools to find an analytic solution to it, but that doesn't mean we can't say anything about the behavior of that model. Okay, so for a differential equation, these are just equations that involve derivatives. So with algebraic equations, we typically have input, output, or maybe several inputs and one output. But inputs and outputs, they're all numbers, values. So with a differential equation, what we're describing is some equation that's telling us how the rate of change of this function is behaving, or how the second derivative is behaving. So here's an example of a differential equation, and just some terminology is that we would call this differential equation a second order differential equation because it involves a second derivative. So differential equations have we can classify them according to several properties. And one of them is what is the highest powered derivative that appears in the equation. That derivative would give us what is the order of that differential equation. So in some sense, it's almost like the degree of a polynomial. And when we're looking at these differential equations, one thing that I want to point out here is it is useful to think about inputs and outputs and which thing is a function of which. And so when we see the derivatives written like this, I can see that right, derivatives are change in output over change in input. So from this, I can see that x is going to be our output and t is going to be our input. And so in the end, what does a solution to a differential equation look like? It's going to be some function that when I plug it into this equation, both sides give me the same value. So we can check this, and we'll get to some of these later today. The way that we check for a solution is similar to algebraic equations, is we plug it into the equation, do the operations the equation tells us to do, and then we check to see whether we get the same thing on both sides. And it's just that when I plug my solution into the equation, the operations that we're going to need to do now are going to be calculus operations. Take a derivative, take a second derivative, add those things together. Okay, any questions? Okay, so here's the first problem that's on that worksheet that was posted up in Canvas. What is a differential equation? So the differential equation that I just had up on the previous slide, that second order differential equation, let me just say that comes from setting up a model for what's called oscillating spring. So we'll get to that shortly this semester, but that comes from a real practical situation. In this example, we're looking at a couple of what we would call systems of differential equations. And we'll also study these towards the end of the semester, how to solve them at least. So here, what we've got are actually a system of two different differential equations. And so we have two outputs. One output is x and one output is y. So these are denoting like the populations of two different species. And they're both changing with time. So that's what this is telling us over here. So population X is changing as time goes on. Population T is changing, Y is changing as time goes on. And what you want to be careful about is if I know what the population of X and Y are at a certain time, when I evaluate these equations, by plugging in certain values for X and Y, the number that I get is not telling me what is the value of X, right? When I plug in values for X and Y and evaluate this expression, it's telling me the rate that population X is changing. So these dx's, dt's, and dy dt's, they can be positive, they can be negative. These populations can be increasing, they can be decreasing. The values for X and Y would need to be positive because these are representing populations, but the derivatives could be negative. So what we're looking at here are two different systems. And let me clear some of this out. And one of them is representing species that are cooperating. One of them is representing species that are in competition with each other. So what I'd like you guys to do is think about which system do you think is the cooperative one, which system do you think is the competitive one? Good, so I hope you enjoy working in those breakout rooms. I just want to introduce us to some of these different features that we'll be using. Okay, so I'm going to open up a poll. Curious what you guys thought. So this is another thing that we'll use. Is just a little polling here. So these are anonymous. I don't know who says what. There's no grade involved in this. Just looking for some quick checks on how this is going. So you should see a little poll pop up. One question: which of the systems is the cooperative system? Okay, so looking at the responses that have been coming in, a few more, take another 10 seconds if you haven't gotten your vote in yet. Okay, thank you all for your responses. So most people thought that system 1 was the cooperative system, and that is correct. That's right. So this is the cooperative, and this one would be the competitive. Does someone want to summarize what came up when you were talking with your classmates as far as how you identified which was which? Feel free to speak or raise a hand, or I've got a random generated list. Oh, Kirsten, excuse
Yes,
me.
Kirsten, yes.
Yes.
So we were discussing that as you increase both X and Y for the cooperative system, system 1, as over time, both X and Y increase, versus in system 2, over time, they end up both decreasing. So the population over time ends up increasing for system 1.
Yeah, so let me try and summarize that. Let me know if I heard you correctly. That's right. So if you're looking at this system over here, increasing X is a little bit more complicated for this one, because in some sense, there's a part of it that's going down and a part of it that's going up. But certainly you can see that if we increase X, looking at this equation over here, we can certainly see that the larger X is, the more the positive the rate of change of Y is going to be, right? So for a large value of X, that's going to make dy dt positive. Dy dt positive means the population Y is increasing. So basically, if we have a lot of X, that's actually good for population Y. And so that would be a cooperative sort of relationship. And we could reverse the same. And over here, we could say, okay, population X. What happens if population Y was large? Well, that would cause population X to increase. So that's a cooperative relationship. Compared to this model over here, that's right, where you can see if I'm looking at this top equation, if we have a lot of Y, that's actually bad for population X in this situation. Okay, so good. So I think definitely being able to look at a differential equation and interpret it in practical terms, like what is these X's and Y's, they actually are representing quantities. And so these symbols all should have some practical meaning, and it's important to be able to see that when we're reading these. So almost all of the examples we're going to be working with in this class, as it should be, are going to be actual models that we're going to base off of something. And so that actually is not just more interesting, but it actually helps the mathematics when you can connect some physical quantity to the symbols, and it might make the operations make a little bit more intuitive sense. Any questions about this example? Okay, so let me then go into the worksheet. And so most of the time we're going to be working with going through some of these worksheets together in class that are posted. So we just talked about the first question. So here was the first question. So let's kind of take a step back and simplify things a bit. So rather than think about two populations that are interacting with each other, let's just think about one population, okay? In this case, fish. So we're gonna let P over here denote this population of fish with respect to time. And we're gonna make some assumptions about the fish, okay, in the lake. So we're gonna say that there's only one species of fish in the lake. So in other words, they don't have any competition for the food supply. Yeah, so the species are actually native to that habitat, so they're not an invasive species that might die off. So they're in a natural environment, and they have access to unlimited amount of food. And this species reproduces. So what I'd like you to do is just sketch a graph of what you think it's going to look like. So for example, let's say we say that at time 0, we start at 10, which is what this is saying over here. What's the graph going to look like? Is it going to look like this? Is it going to look like this? Is it going to look like this? So I'd like you to just come up with, what would your best guess be for what the solution would look like if we start at 10, if we were to start with 20 fish at time 0 versus if we were to start with 30 fish at time 0. And here's another thing we can try doing. We have a whiteboard. And in theory, we all can draw on this whiteboard. Does anyone want to? Here we are, let's say at 10. It's a little bit harder to draw with my finger. Does anyone want to draw their graph on this? Let me know if you're unable to, if you try to. I'm just curious how this, I'm going to play with all these things that we can do in Zoom, see what works. So I believe these should be interactive. Is anyone trying to mark it up?
I'm not able to.
Okay.
I don't know how to. But.
Yeah, that's probably, oh, somebody did. That's cool.
That was me. So apparently at the top of the screen, there's like an options. Options. You click on that and then you can select a thing that says interact or something like that.
So say that again. Sorry, Cortez.
At the top of the screen, there's a bar that comes down and says view options. You hit annotate on that, and then it picks up like the place where you can draw.
Yeah, that's right. There should be a little button that says annotate. Yeah, and or for me it says whiteboard actually, and you can click and unclick that and mark it up. So I did see that somewhere there, but then they disappear. So hey, there we go. Thank you. So I'm seeing a lot of these. That's right. So let's kind of just think about what people are drawing here. They all pretty much look the same. So I'm just going to make some comments about what I see here. So first of all, these things are all going up. So you're all saying that the population is going to increase, and going to increase forever by what I'm looking at here. And in fact, as time goes on, the graph is getting steeper. Though someone just drew a linear one, sort of, the graph is getting steeper. So what that is telling me is that the rate of change, dp dt, is getting more and more, should be getting more and more positive. Okay, so remember, what we're trying to do is not come up with an equation for the graphs that you're drawing, but we're going to come up with an equation for the derivative of the graph that you're drawing. Okay, good. So these all look really reasonable pictures. Any questions before I go back into the worksheet? Okay. Is there a question? Okay, so good. So we're saying that I saw pictures that looked like this, and then they kind of looked like this and like this. Okay, and I think we kind of commented to some extent what's happening to the slope as time goes on. Here we're saying that we can see dp dt is positive since the population is increasing and getting more and more positive. So what we'd like to do, say down here in part 3, is come up with a formula for this differential equation. And this formula, if you kind of recall the system that we looked at prior, okay, it might depend on t and it might depend on p. So the rate at which the population is changing could depend on time, and it could depend on what the current population of fish are right now. So that's what this problem is getting at over here. So we'd like to figure out what this formula is. And the question is, do you think that this rate of change depends on time, depends on the population of fish, or it's going to depend on both of those things? And here, what's one thing that you might be wondering is this p that I drew over here is a function of t itself. But we usually don't write that here. We're thinking about t and p and just know in the back of your head that p actually is changing as time changes. And that's exactly what this differential equation is going to model for us. Okay, so I'm going to just open up a poll, see what you think about this. So for this model of dp dt, the options are that I think the rate, and let me try and state this in practical terms. I think the rate of change of the fish population is going to depend on time, how many days later it is. I think the population of fish is going to depend on, or the rate of change of the fish population is going to depend on how many fish are currently around, or is it going to depend on both of those things? Okay, I'm gonna close it out in about 5 seconds. Okay, so here were the results from the class. So most people thought it's gonna depend on both P and T. And some thought P but not T, and some thought T but not P. So let's start with, well, let me just open it up. Does anybody want to share what your thinking was when you answered this question?
Just looking at that, like what you annotated on there, dp dt, the is a function of t and p. So I was thinking that it would be both because you like two variables in that function, population and time.
Yeah, so this over here could depend on P and T. That's right. It doesn't have to. And so one thing that you might want to consider when you're answering question 3 might be, let's just fix a time, 1 second, or excuse me, let's say like 1 day later. Let's say T is measuring days since some initial time and P is measuring how many fish are in the lake at that day. So if we're at 1 day later, and let's say we've got lake 1 that has 30 fish in it, and we have another lake, same exact conditions, but this lake has 10 fish in it 1 day later. Which population of fish do you think is going to grow faster, or do you think they're going to grow at the same rate? Yeah. Person.
The lake with the population of 30 is going to grow faster, even though they're both at the same time.
Right. Why would a lake with more fish, why would you expect that to be growing faster?
There are more breeding pairs.
That's right. So every time fish interact, or at least male and female, there's some potential for reproduction. That's right. And so the more fish that we have, the more interactions we're going to have, the faster we might expect that population to grow. So if this means, if we were to fix a t-value, what we can see is that dp/dt does change based on what the current fish population is. So this differential equation, certainly dp/dt is going to depend on the fish population. The more fish we have, the faster we would expect that population to rise. So we are going to have some dependence on p. And now let's think about this. So now let's think about another situation where we've got, here's lake 1, and we're going to say at time 0, this lake has 20 fish in it. And here's some other lake, and it started at time 0 with 10 fish. And then 3 days later, they now have 20 fish. And if you want to think about if we want to compare the rate at which these two fish populations are changing, right? The fact that we started calculating our population from some benchmark day, which is pretty arbitrary, doesn't really tell us anything, right? It doesn't really, if I know that this has been 3 days since we've been taking fish measurements, that really doesn't tell me much about how the fish population might be changing. So if we're in this case, where here are 2 lakes, okay, one of them started with 20 fish, the other one started with 10 fish, but 3 days later, it now has 20 fish. These 2 lakes would have fish populations that are growing at about the same rate. And so it's not so much what day or how many days later are we measuring the rate of change, it's more how many fish are in the lake right now. That's what's going to determine how fast the population is changing. So this differential equation is only going to depend on p. Okay, and for those of you that said it's going to depend on p and t, what you might be thinking is that the value p, the population of fish, that certainly changes with time. We can see that in the graph. But the rate of change of the fish only really depends on how many fish are in the lake at that moment. And so based on the graphs that a lot of you were drawing up here, we would want to find a differential equation which is always positive and getting more and more positive as p gets larger. So there are all sorts of different possible models that could work. Here's one that would work, for example, right? Since p is the fish population, p is always positive, and as p is increasing, that means dp/dt would be increasing as well. So this would be maybe like the simplest model that would satisfy those criteria. I will say that the actual model here looks like this for some constant value k. So what is true about populations that grow under these conditions is that we would say what this differential equation is saying is that the rate of change of the population is proportional to the current population of fish. Any questions?
That makes a lot more sense. Thank you. I see now how you're looking at it. It makes more sense.
Okay.
Yeah.
Yeah, and it's maybe there's like a subtle point here that is you might be thinking, well, P depends on T, and if the differential equation depends on T, then okay, it by definition depends on T. But here it's a little bit different. All we're saying here, that's right, is that the rate of change of P only depends on what is the current population of P and nothing else. That's a bad assumption to make over a long term. We've made a lot of really simplifying assumptions here that we're gonna get rid of and come up with a more reasonable model. Like there probably is some competition. You know, fish do die. They don't just keep on living forever and so on. So we do need to take those sorts of things into account. Okay, so just to kind of define things before we end for today. So yes, differential equation is an equation that involves derivatives. We're not all that creative when we name things in math. And so here are a bunch of examples of differential equations. These are all first order differential equations, just so you know. Since all of these differential equations, the highest derivative that appears in the equation is the first derivative. So as you might suspect, rather than start this semester studying how do we solve 8th order differential equations, we start with first order differential equations. We learn some techniques that work for those. Then we jump up to higher order differential equations and see how we might need to tweak those methods for higher order differential equations. But some of these differential equations are things that you may have already seen in a calculus class that you may think, well, I know how to solve this because I know how to integrate things, and that's right. So yeah, so the question here is, what are solutions to differential equations? How can we check that we have solutions? Are these solutions unique? So these are some of the ideas that you might be thinking about. So here the question is, here's the differential equation. And what I'd like to know is this thing a solution to that differential equation? And the way that we check it is we take this as if it were a number and we check the left side. What happens when I plug this into the left side of the differential equation? So on the left, right, we would say, take the derivative of y. I'll just use my prime notation. So we would say here, y prime, derivative of y, and here this means with respect to t would be 2. And then I plug this into the right side. And I think, okay, do I get the same expression on the left side and the right side when I plug this in? If I do, great. If I don't, then it's not a solution. And the thing that you want to be careful about here is that we're going to need the left side and the right side to be the same for all values of t. So now I'm going to plug this into the right side. So the right side says, right, we're going to take y, which is 1 plus 2t, and square it, subtract 1, and then divide by t squared plus 2t. Okay, again, all we're doing is we're going to take y, and every place there's a y in this differential equation, I'm going to plug in my suggested solution and do the operations that it tells me to do. So again, on the left side, the operation was calculate the derivative. That's how we got 2 on the left side. And then on the right side, it's an algebraic expression. So I just plug in 1 plus 2t in place of the y that was in the numerator. And then we would want to simplify this. So the 1 plus 2t squared, you can check my algebra here. I believe I would get something like this. And then we have some nice cancellations, right? So here we could say that one cancels that one. And so then what we've got left on the top is 4t plus 4t squared. And on the bottom, we've got t squared plus 2t. So any questions? And so just because they don't look the same doesn't necessarily mean we struck out here, because we can simplify this some more, right? So here I could, factor a t out of both sides or something like this. So I suppose what I could do here is mostly just cancel a t out from the top and the bottom. We get left with something like this. And yeah, this might work for some values of t. I plug in some values of t and I might get the same thing that I got on the left side, but I'm not getting the same thing for every single value of t. So in this case, we would say this is definitely not a solution to the differential equation. Okay, so I'll stop here since we're just about out of time.
But is it a solution? You said it's a solution for specific values of t. Is that possible? But it's not a solution for all the values of t.
That's right. So we would say that this thing over here, it's only going to be a solution is if the left side and the right side are equal for every single value of t. And since this works for some values of t, but not for other values of t, this is not a solution. So I'm gonna stop here. If you have any questions or you want to hang out afterwards, you're more than welcome to do so. I would encourage you to give part B a look over, and questions 5 and 6 we can talk about next time if you like. But for these, you could solve these by integrating both sides. For example, that's the idea here, to practice some integration. There was a question, Cortez?
Yeah, so just for the next class, so that I'm sure what we're doing, we have the small reading quiz to do beforehand, right?
Mm-hmm.
And then watch the videos you post?
Yes. Yeah, so there's no written homework due before next class. So there is a homework assignment that's open. That's not due until next week, but there will be a short reading quiz to look at before Wednesday. And so that reading quiz is going to be on section 1.2 of the notes. And then in class, we'll talk about section 1.2 and section 1.6. So 1.6 we'll do together. You don't have to read about that in advance, but you're welcome to if you want to. Okay, well, thank you, everybody. Nice to meet you all. If you have any questions in the meantime, I would tell you to stop by my office. If you happen to live close by, you're welcome to. Otherwise, just shoot me an email. That's certainly the best way. I'm online most of the day, so I'll get your message. But enjoy the rest of your classes, and I will see you all on Wednesday.
Thank you.
Yep.